Okay, let's move on to the second part of this practice problem on unit hydrographs where we actually use the unit hydrograph we just calculated in the first part. So the first thing I'm going to do is I'm going to do all this work in the second worksheet down here, which is called application. See that down there? So the first thing I need to do is copy the hard work I did in the first part, which is my unit hydrograph, and I'm going to copy that into the second. Actually, what I'm going to do here, let me just copy the actual data here. So I'm going to copy the numbers here that I just derived, and I'm going to copy it into the second. I'm going to copy that. I'm going to copy that into here. And now when I copy that, I'm going to go to right click here, and I want to copy the values. And the reason I need to do that is if I don't do that, then I'm copying formulas and they won't make any sense and I'll get lots of errors. So having calculated the values, there you go. So here's my unit hydrograph. I've just successfully moved it from my first worksheet to my second worksheet so that I can now use it. So let's see what we've got here. It might be a little confusing. Let me try to explain what happened. So in these first 5 columns here, I'm showing the precipitation that has occurred during 5 straight hours. So the first hour, we have the storm starts, we get 0.13 inch of total precipitation. That's not effective, but total precipitation, and then 0.16, 0.19, 0.15, and 0.04. I first have to calculate the effective precipitation, and I'm going to do that using that value of effective precipitation to precipitation total. Remember, I calculated that in the other page. Actually, let's just grab that as well too. Um, where did that number come from? It's right over here, right? So I'm going to copy this just so I have it over here. There it is. Copy the value here now, right? There it is. First thing I'm going to do is calculate the effective precipitation. And then once I know the effective precipitation for the first 5 hours, what I'm going to do, this is my timeline of what's happening. So the storm starts at time 0. In the first hour, we're going to get this amount of the amount of precipitation 0.13. In the second hour, we're going to get 0.16. The third hour, etc. So this is now going to be our governing timeline for what happens during this stream. And for each column, I'm going to enter using the unit hydrograph the contribution from this hour of effective precipitation to the total storm discharge, the total event flow discharge of the stream. So first thing, let's just calculate the effective precipitation, right? So remember, this is just going to be equal the value in B2 times this constant that I derived here. So there it is with many more significant figures than I really need. So let's just make it a little bit less awful. There we go. So I'm just going to copy this across. So now I've calculated, oops, that didn't, this is a good lesson here. When I copied it, notice what happened? Because I didn't specify that H2 was an absolute reference, when I copied it, it moved the reference. So what I really need to do here is modify this to, there it is. So I want $H, $2. So now when I copy this equation, then it will still always refer to H2. Yeah, there we go. So it takes F2 times that conversion factor H2. And so here we have these values here now represent my effective precipitations. I'll make them a little bit darker there, that are driving the unit hydrograph theory, right? So in the first column here, we're going to put the response of the stream to that first increment of effective precipitation. And so remember that the unit hydrograph is for 1 inch of effective precipitation, but during this first hour, we only got 0.0840 inches. So we have to scale the unit hydrograph by that number. So what I'm going to do is in 0 here, the value here, this is K, this is cell K3. So I'm going to take equals K3, that's the response of the unit hydrograph to 1 inch of effective precipitation, and I'm going to multiply that by the value in cell B3. I'm going to use $B, $3, because I don't want that to change when I now copy this equation all the way down. So this is just copying that first unit hydrograph all the way down. So there it is. This is the response of the first increment of precipitation using our unit hydrograph. Now, after the first hour, the second hour is characterized by another increment of precipitation. It's 0.1033 of effective precipitation. And now I want to do the same thing. But notice now we're delayed an hour because this is the second one, right? So we have to start the unit hydrograph, shift it an hour later. So I'm going to take K3 again. This is my unit hydrograph times now $C, $3. That's the effective precipitation during the second increment. And I'm going to do exactly the same thing. Copy down. And so for the third one, it's going to be equal K3 times D3, right? Copy it down. And there I finished the rest of the columns. And notice that each column is offset by an hour, right? Because the precipitation that drives it occurs later. So these then are the contributions from each hour of precipitation scaled by the effective precipitation using the unit hydrograph theory. And what I want to do now is simply sum up the contributions from each of the 5 hours to the total storm flow or event flow or quick flow. So what I'm going to do simply here is sum the values in cells B5 to F5. There it is. Nothing there in the first hour, but I'm going to now copy this down. And this really is what I want. This is now the total discharge in the stream that I see as a result of all 5 increments of effective precipitation using the unit hydrograph theory. So this then is my hydrograph. And to get my actually plot my hydrograph, I'm going to plot time, right? This is, we always plot time versus discharge, and then this is going to be event discharge, right? So there's time versus the event discharge, event flow, quick flow. There it is. And I want to now plot these. I want to insert a graph, and I'm going to choose one that has nice, beautiful curve like this. And I'll just put it over here. There's my hydrograph. That is the storm, that is the event hydrograph that I predict based on the precipitation event, that 5-hour precipitation event in the watershed. Is this actually what I'd measure at the stream? No, because in addition to the event flow, there's also some amount of base flow which is being fed into the stream. Remember, we stripped that out when we calculate the event flow. So the actual discharge of the stream will be somewhat higher than this because we have to add the base flow contribution to the stream. This is just the event flow. But in many cases like this one, it is probably the great majority of the discharge. Now, one of the questions is, where does the peak flow occur? And what is the peak flow, event flow in CFS, and when does that occur? So let's look at this is my storm peak discharge. The storm flow or the event flow or the quick flow. Let's just give it a funny color here. So it's in blue. Okay. So let's look at where the peak discharge occurs. It looks like it's going to be right here at 574 CFS. There it is. That's the peak discharge, storm flow discharge, and it occurs 6 hours after the onset of the storm. So that's one of the questions we had to answer as well. So there you go. We have applied the unit hydrograph that we derived in the first part to this storm, and we predicted the event flow of the storm. Notice that with this theory now, I could do this for any storm as long as I have measurements of total precipitation per hour for any storm. Maybe it lasts 2 days. It's a drizzle over 3 days. Doesn't matter. We could just use this exact same procedure to predict the event hydrograph based on any sequence of hour-long precipitation events that drive the storm discharge.